So first of all, thank you for these great talks and thank you for the invitation today. So what I would like to talk about, so that's the title, Tectonic Controls on Melt Production and Crustal Architecture During Magma-poor Seafloor Spreading, which is the title of the paper that has been published in EPSL. So this work has been carried out at the University of Bremen at Marum. So sorry, I will put that out. At Marum Center in collaboration with Javier Garcia Pintado, Marta Perez Gusinier, Zhonglang Liu, Wolfgang Bach, and Mathilde Kana. So what I will focus particularly on ultra-slow spreading ridges, like at the southwest Indian Ridge, but we also observe them in the Gakel Ridge here, and how the magmatic and tectonic and faulting and hydrothermal processes can interact together to shape crustal architecture and relate to melt production. Next. So yes, seafloor spreading starts after continental breakup, that is shown here in this sketch. And so as the seafloor spreading progress, the deformations migrate from the continental rifted margins toward the narrow region, the ridge axis here. And here we have this spatial and temporal interactions between magmatic, tectonic, and hydrothermal processes that will shape the ridge morphology and the crustal architecture. And so at slow and ultra-slow spreading ridges, this leads to a wide diversity of architecture. So we have wide valley in the magmatic domain with a magmatic crust. And in ultra-slow and slow setting, we have this detachment faulting that accommodates the extension and will exhume a mixture of magmatic rocks and serpentinized peridotite. And this serpentinization has gathered significant importance for its role as it's at the ocean continental transition zone to produce hydrogens. And also so this, I invite you to look at this new paper, so how hydrogen productions can link to detachment faultings. So this this variation in crustal architecture has been documented along the ridge axis, as illustrated here at the magma mid-Atlantic ridges, and also across the ridge axis. So what we have is that the combination of geophysical and geological observations will reveal this spatial variation in terms of seismic velocity and also in terms of gravity anomaly. And when this variability is translated in terms of crustal thickness, it is usually assumed that we have a thicker crustal sections that relate to magmatic accretion and an increase in the melt production. And thinner section is commonly attributed to more tectonically spreading ridges with formation of large expanse of serpentinized mantle. So this variability in the crustal thickness, in the geophysic crustal thickness, reflect this change in melt production rate. So the variability, the fluctuations in melt productions has been documented also by geochemical studies that show we have the degree of Opoling mantle, of melting of Opoling mantle that fluctuate with time over a period of 2 to 4 million years. And the origin of these fluctuations is attributed to mantle heterogeneities, potential mantle temperature, and spreading rates. So, but if the 5 to 10 kilometer wavelength crustal thickness variations reflect temporal fluctuations in melt production, with thick crustal section reflecting larger volume of magma, we can ask what mechanism could drive such a variability in a long-term low melt supply regime, which is documented in the well-studied ultra-slow magma-poor eastern corridor in the southwest Indian Ridge. So here we have, so the dominant lithology is serpentinized mantle. The seafloor is, so this smooth seafloor is shaped by a successive detachment faults that is represented here with a pink color. So that's the smooth seafloor. So this is a combination of different observations. And we know that this region is record a low melt supply for almost 11 million years. So the crustal, the brittle lithosphere here is characterized by thick brittle lithosphere up to 10 to 15 kilometers. And the seismic observations show that we have this ondulation across the ridge axis that are shown by this 7 kilometers second. And given the low melt supply regime, the interpretation is that the variability we observed is related to serpentinization extent to depth. So that's what we have addressed in this study using a 2D viscoelastoplastic model. So the code is the Rift to Ridge code, which is developed at the University of Bremen within the geophysics geodynamic group. And so the model includes several components that I will be happy to talk later. So we have decided to start to form a mature ridge system, not by starting with a pre-imposed ridge thermal structure, but from the full evolution from continental rifting, continental breakup, and then the development of a mature ridge system. So here you see the final evolution. So we have the continental margins, the oceanic plates, and the spreading center here. So for the rest of the presentation, I will focus here and I will detail more what do you see here. So let's go back to the observations. So that's the model results. So we zoom on the ridge on the ridge axis. So what do you see here? In the green is shown the degree of serpentinization. We have active faults here that act as a fluid pathway, so hydrothermal cooling occurs along active faults as well as serpentinization. We have the magma that is produced as the mantle rise and decompress, and so the thickness of the dike, the current dike is shown here in blue, actually reflect the volume of magma generated at each time step. We have the accreted magma that is represented by these orange markers. So these lines here with the circle represent the crustal thickness, which is calculated to be actually which correspond to the volume of accreted magma plus the volume of serpentinized mantle. So there is an important thing to say before starting. So you see we have the magma that is on place at different depths. So to do that, what we did actually, we have assumed that the serpentinization front will act as a barrier for the propagating dike. This dike will travel vertically up from a region when it is produced at the depth, and the X location is defined by the shallowest depth of the 1,001 degree isotherm. And studies have shown that when the dike propagates and we cut through rocks that have different rheological properties and mechanical properties, this can perturbate the ascent of the dike and eventually lead to the arrest of the dike. So this is what we suppose happened here. The melt is going through fresh mantle and then serpentinized mantle that have distinct rheology. And in addition, the serpentinization has been shown to have a brittle non-dilatant behavior. So all these factors led us to this assumption saying that the serpentinization front will act as a barrier. So what you see here, so when you compare now to the observation, that's the observed bathymetry, that the bathymetry of our model, so we find good agreement. So for that, we were happy. We have also the fault offset. So here we have this flip-flop, and I will show you how it evolves. And so fault spacing that are well reproduced. And the ondulation in the 7 kilometers second of the iso velocity is well reproduced by our geological crustal thickness.
You're now at 10 minutes.
Yeah, thank you. So the evolution of the model we'll see, so this flip-flop occurs with a horse phase. We have conjugate normal faults that will connect at the surface, and then we will have one of these faults that will be the dominant and form the new detachment phase. So that's the model evolution. So what will happen is that during the horse phase, because the extent in depth of serpentinization is limited at the center of the host, that will allow the magma to accrete at shallower level. And during the detachment phase, we have cooling that favor the extent of serpentinization, the widespread of serpentinization, but also the extent in depth of this serpentinization that leads to deepen the magma emplacement. And in terms of a compositional crustal thickness, because we are in a low magma regime, the volume of when it's only magmatic accretion during the horse phase, that will lead to thin crustal section, while during the detachment phase, we have a thickening of the crustal thickness. This reproduces the observations at the Southwest Indian Ridge, but now we can ask how that can relate to melt production rate. So when we analyze the relationship between a detachment faulting and the upwelling mantle velocity, what we found is that during the horse phase, the mantle flow is focused in a narrow region, and this leads to an increase of the upwelling mantle velocity that will then increase the geotherm. And this increase in geotherm will have an effect on the melt productions that will lead to increase the melt productions, as shown here by the black line. We have a higher melt supply, a higher melt thickness. During the horse phase, what is happening is that the asymmetric flow of the mantle will follow the detachment faulting, and the domain where the mantle is focused widen. And this widening will lead to a decrease in the upwelling mantle velocity that then will lower the geotherm. And as a consequences, that will result in a decrease of the melt supply. So here the gray color show the vertical velocity, and you see that where we are in a dark, very dark, we are faster than when we become gray. And when we go again to the horse phase, this is again, we are back to a phase of higher melt supply. And we found 8% change over a period of 1 to 3 million years, which coincide with the detachment faulting activity. So to conclude, in this context of long-term low melt supply regime and during flip-flop detachment faulting, so we have the crustal thickening that actually correlate to the increase of the extent in depth of serpentinization and widespread of serpentinization, which is actually anti-correlated. So this compositional crust thicken, and the thickening of the crust is anti-correlated with melt production rates, which is actually decreasing, that is shown here, because we are widening the system becomes colder, the upwelling velocity decrease, and that leads to low melt supply. So the temporal variation in melt production rates are here due to change in upwelling mantle velocity that are controlled by the faulting mode. And so we suggest that the geophysical crustal thickness ondulations in such context can reflect spatial variation in serpentinization rather than fluctuation in melt production, which are instead anti-correlated. So if we look at this along axis and a cross axis variation for over the 10 to 20 kilometer, so this might actually reflect asynchronous, the different snapshots of the spreading in this low melt supply and cold environment. Thank you.
Thank you, Leila. That's a fascinating talk. If people have questions, please put them in the chat. I have a question. I'm kind of fascinated by this idea that the serpentinized mantle would act as some kind of shielding barrier that would prevent the melt from kind of percolating up. But then you went on to say that, it would be quite brittle. So wouldn't that enhance the amount of pathways that the melt could take and do the opposite?
Well, that's these assumptions came from different bibliography, so from laboratory studies, from theoretical studies, and geological observation. That's the thing is, so this dike they open in the mode 1 like that, so they need to make their space, and how do they make their space also depends on how the surrounding rocks will respond. So if we have a small volume of magma, so means that not such a lot of strength to open, if the surrounding rocks are always changing their properties, I think that the energy cost to accommodate this change is too much, and I guess the melt would just either follow a path if it found something easier or just stop. So for simplicity here, we just said, okay, when they found this very widely serpentinite mantle environment, they stop.
That's very, very cool. Okay, I can see Sasha's got his hand up.
Follow up to this one. In addition to the explanation that you gave, the upper part of the footwall should be in compression because you kind of unbend it, and that's why you get your big normal faults at the base of your model that I saw before. And so the upper part should be consequently in compression, which would be like preventing the dikes to pass through. Right here, you see the big X in the middle. This is extension, the extensional component of this kind of apparent unbending, and the top part should then be in compression. And if you look closely in the stress field, I think you would see that as well.
Yeah.
My question is actually related to that. There's a big kind of density contrast between the intruded dikes and the serpentinized layer, right? Wouldn't you see that in geophysical measurements if you have some seismic lines there to see the top zone where the dike's in place and where the serpentinization starts? Is this something that would be visible?
Well, I guess, I mean, here in this environment, we have a very low volume of melt, and this is more, I would say it's more dominated by alteration. And on top of that, we are coming to, at least 2 kilometers, 3 kilometers, there is a lot of hydrothermal circulation coming up and everything is altered. So to see their clear signature in seismic about if we have a few volume of melt, maybe these seismic reflectors, if we have high resolution, can tell us about melt infiltration or seals, but in terms of density contrast, I'm not so sure that we can really see them in this environment. But I'm not an expert of that, so I don't know.
Right, thanks.